Welcome to this introduction to Boolean algebra. This is an important concept in electronics and computer science. It allows us to come up with some general rules for how we represent the system of behavior and modify any circuit design to make it simpler. We will see some simple rules, but Karnaugh maps are still a go-to choice. We have some basic operations. These can often be confused with symbols in algebra learned in maths. However, it is important to remember that this is algebra for logic, and so has a few different rules and symbols to get used to. We can see that a plus sign often denotes an OR gate, a dot often denotes an AND gate, and a bar often denotes a NOT gate. When we design circuits, we are only interested in the events that give a true output. This is because it captures the behavior of the system in a single equation. This final expression is called the sum of products. We can see why, as each of the innermost AND gates are the products, and we have an outermost OR gate. We have it in this form, as each product term represents a true output for some, but not all, of the behaviors of interest. Hence, we must now use an OR gate to give the final output as true when any of these AND gates are true. The OR gate allows us to not require any particular combination of innermost AND gates in order to output true. These are some common and useful identities to use in Boolean algebra. The main point of this type of algebra is to simplify and get as few gates as possible, or realize a sum of products expression using only a certain type of gate. We start by stating some obvious points. 1.a says that the output is only true dependent on a, as the other input is always 1. The next rules show that the order of combination in AND and OR gates does not matter. The next rule shows we can expand brackets as we are used to performing in regular maths. After this, we can see that if we have inputs of A and A naught into an OR gate, the output is always true. If we pass something through a NOT gate twice, we get the original signal. In a similar way to the previous rule, if we have A, then A naught is the opposite, so when passed through an AND gate, the result is always 0. This final rule is DeMorgan's law. This is useful to break a NAND and NOR gate into terms that can be simplified. Although we won't derive these here, the good thing about logic is that we can prove all of these identities by considering the truth tables and comparing. A helpful tip is that it is often simpler to transfer each sum of products expression to a Karnaugh map in order to ensure we have simplified as much as possible. Often, expressions come as half simplified, making it difficult to put directly into a Karnaugh map. As we can see, if we have only 3 variables, then a minterm is a sum of products term that contains all 3 variables. However, this second term is not complete. If we have the complete minterms, then we can fill in the Karnaugh map. The use of one of the identities previously mentioned helps with this. This demonstrates how we fill in the Karnaugh maps from the minterms expression. The product expressions refer to the labels on the top and side of the map. For example, the combination 1, 0 refers to when A equals 1 and B equals B naught or 0. The right-hand column refers to the combinations 1, 0, 0 and 1, 0, 1, with minterms AB naught C naught and AB naught C respectively. We conclude with some final remarks. This video has introduced the basic identities used in Boolean algebra. These can be used to simplify expressions, but Karnaugh maps are a preferred method owing to their simplicity in complex cases. Like and subscribe for more.